It's my pleasure today to introduce Mikhail Katz, who will be telling us about collapsing surfaces. Thanks, Misha.
Okay, thank you very much for the invitation. I would like to speak about collapsing surfaces. Collapsing surfaces, collapsing manifolds, or more general Alexandrov spaces, is a fairly active field today. So we will denote a space that we want to collapse by M, and the space is being collapsed to by X. And so here the name of the game is that you work with lower curvature bounds. Curvature is only bounded from below, not from above. When the curvature is bounded from above, of course, it's a much stronger condition with much stronger results. Gromov compactness theorem, that sort of thing. And so the collapsing occurs in the sense of the Gromov-Hausdorff distance, which I assume I don't have to define in this seminar. So what we're talking about, is a situation where M collapses to X, which has lower dimension than M, and the Gromov-Hausdorff distance between them tends to 0. That's what it means to collapse. And so here, one of the seminal texts is the paper by Shiohama and Yamaguchi, the earlier paper by Yamaguchi. And so the case of surfaces, when M is a surface, can be thought of as a baby case of the general theory of Shiohama Yamaguchi, which is actually was never written down. Shiohama Yamaguchi's paper is mostly dedicated to 3 manifolds. So the case of surfaces literally has not been written down. And Semyon Olesker was one of the people who was asking about various questions about surfaces. So in particular, there's a conjectured formula that Olesker conjectured that involves a stratification of X. So here there's a well-known thing that wasn't invented by Olesker called integration against the Euler characteristic, or more precisely, discrete integration against the Euler characteristic. So what's involved is first and foremost, one needs to justify the following principle in order for this conjectured formula to even begin to make sense. That for every point in each, so X is going to be a certain stratified space, not necessarily a manifold. And for all the points in each stratum of X, as the collapse takes place, then small metric balls in M centered at P have a well-defined homotopy type. So that's the very first thing that you need to be able to justify in order to even start talking about this formula. And so let's go on. So at least if you can't control the homotopy type, at least maybe you can control at least the Euler characteristic. That would be necessary in order to start talking about the formula. And in any case, the homotopy type should be independent of the point, P, and of the radius of the ball. So the radius is assumed to be small, but in any case, for a sufficiently small radius, the homotopy type should be independent of the radius. So we will talk about the case of surfaces collapsing to a one-dimensional complex, which could be either a circle or a segment. And the results that I'm going to talk about are certain progress in the direction of conjecture of Olesker's that appears in a paper of his from 3 years ago. And so let me first of all talk about some earlier work. In the case of the Taurus, what one can show is that the Taurus cannot collapse to a segment. So you can think of a Taurus as getting thinner and thinner and turning into a circle. So that's certainly possible. But it cannot collapse to a segment in the sense of the Gromov-Hausdorff collapse. So I proved this in the paper of mine that was published last year, using various techniques, GaussManet and Borsa coulomb, and the Shiohama critical points of distance functions. So this theory of critical points of distance functions is a kind of a generalized Morse theory. That's, of course, the foundation of the Yamaguchi theory as well. Shiohama Yamaguchi theory. But the original paper appeared already in the 70s and was published by Grover Yamaguchi, by Grover and Shiohama. And also Zamora, also last year, he proved this fact about the Taurus, that the Taurus cannot collapse to to a segment, but using different techniques. He used Yamaguchi fibration. I didn't use Yamaguchi fibration. I used more classical techniques. So one thing that I should add here is that perhaps slightly surprisingly, the Klein bottle can collapse to a segment. Taurus cannot, but the Klein bottle can. And this is not something that Zamora and I noticed. It was appeared in this observation appears in a paper by Bettiol and others from 3 years ago on these pages here. And could be there, possibly there are earlier references, but I wasn't able to find any. Anyway, it's a trivial observation, but I haven't found any earlier sources for this observation. Okay, so also we're going to normalize the curvature to be bounded below by -1. Might as well, because this way some of the estimates will be easier to write down. So let's just go. Let me just give a quick overview of the critical point theory. Let us define a taut subset of a sphere as a subset not contained in any open hemisphere. So this is the most elegant definition, perhaps, but a more working definition is to say that the subset is taut even if only for every vector, for every direction in this, which can be represented by a unit vector in the sphere, there exists a point T of the set such that the angle between them is less or equal to pi/2. So that's an equivalent definition of a taut subset. A taut, maybe it would have been better to call it a bulky subset. It's not contained in any hemisphere. In some of my early papers, I used the term taut. I think also some other authors have used the term taut. So in any case, Grover, so this notion will be used in the next definition, next page. So as I mentioned already, Grover and Shiohama developed a theory of critical points of the distance function, even though the distance function from a point in a manifold is not a smooth function, but can talk meaningfully about critical points of such a function. So as you know, the dp, where p is a point of the manifold, and Gromov put them to very good use in his paper on Beatty numbers in '81. Okay, so dp is the distance function between distance between p and x, so we can go on to the definition of a critical point. So a point q in the manifold M is called the critical point of this distance function dp. If the set of tangent directions at q of minimizing geodesics joining p and q is a taut subset of the sphere. So, so to speak, in every direction, when you're sitting at the point q, then, so to speak, in every direction, there's a shorter geodesic leading to p, where every direction means that you can always form an angle, an acute angle with a minimizing geodesic. Acute meaning less than or equal to pi/2. And so the significance of this notion of critical point is the following lemma that appears already in Grover-Shiohama, that if there are no critical points, then you would expect by Morse theory that there would be no changes in topology of the R-ball. And this is exactly what the lemma says. The R-ball, if there are no critical points in the range between, or values between R and S of the distance function, then the R-ball is diffeomorphic to the S-ball. So again, absence of critical points gives you a kind of a deformation lemma that the neighborhoods are diffeomorphic. There's no change in topology, just as in Morse theory. So just to give some quick examples of critical points, if you fix a point P in a manifold M, and then you look at the points which are at maximal distance from P in the manifold, then such a point is always a critical point. That's one example. It's just a first variation argument. And if the manifold is not simply connected, then if you look at the shortest non-contractible loop based at the point P, then that's also always a critical point, simply because here the point T is bulky because it contains a pair of opposite directions, a pair of antipodal vectors, antipodal points of the sphere. That's also called bulky because for every, okay, a pair of opposite directions is also a taut set. And so now there's a convenient language here that I noticed that people who talk about collapse, they sort of tend to work with insufficient vocabulary. They talk about sequences, but really needs to talk about sequences of sequences. And so you sort of get lost in the language of sequences. And I found it useful to talk about three scales instead. There are three scales. Really, in the subject, there are three scales, which I call tiny, small, and appreciable. Tiny scale is the scale of the GH distance between M and X. So M and X are very close. There are tiny distance between them. So to a nearsighted observer, M looks like X already. You can't really tell that M has more meat than X. So then there is the small scale. Then it's going to be the scale of the balls, epsilon balls in M, whose homotopic type you're interested in. So this is the intermediate scales of the three. And then there's an appreciable scale. Appreciable means the ordinary size scale. That's the length or the diameter of X itself. So let's say appreciable scale, you can fix to be 1. We don't want to fix it to be 1 because we want to work with the curvature normalization bigger or equal to -1. So so the appreciable scale is just an ordinary ordinary scale. And so appreciable scale is incomparably larger than the small scale, and the small scale is incomparably larger than the tiny scale. So these are the three scales. It's just convenient language to express what's going on here. So let's first show how the Borsa-Coulomb theorem is used in this business. So we will denote by U delta of A, the delta neighborhood of a set A in the metric space, in some metric space, in some ambient metric space Z. So we have the first level. Let's take two circles and denote them A and B. So A and B are Riemannian circles. And they are of length that's sufficiently large compared to delta, at least delta. And let's assume that they're embedded strongly isometric in a metric space. So strongly isometrically just means isometrically. So the metric space is denoted Z, and the distance function there is denoted by dist sub Z. So then the lemma says that if A is contained in a tiny neighborhood of B, then the inclusion of A into the neighborhood is non-trivial in homology. And B is also contained in the tiny neighborhood of A. Okay, so here it also call A delta tiny. Delta is an arbitrary number here. So we will prove this by a skeletal, by just construction using skeletal, successive construction by skeletal. First, we choose a uniform partition, delta partition of A, a sufficiently fine partition. And then we map each partition point simply to the nearest point of B. We start mapping the circle to another by mapping each point of a partition to the nearest point of the other circle. And if X and Y are successive partition points, then just by the triangle inequality, we get a bound on the distance between their images on B, which is less than 3 delta. And now we can use the linear structure of the segment to just send the segment AB to the span of their images in B. And also, by the triangle inequality, you get the distance between every point and its image in P is less than, is at most 5B. Is at most 5 delta. So it's still tiny. Okay, so now we're ready to show that the degree of our mark that we just constructed is non-zero. Suppose it has 0 degree. If it has 0 degree, then by the usual nonsense, you can lift it to the universal cover of B. In other words, you get a map from a circle to a line. And then by the Borsa-Coulomb theorem, there's a pair of opposite points, antipodal points of the circle A, with the same image of the circle B. And since N and S are antipodal, their distance is less than 10, is bigger than 10 delta. That's because we assume that the circle is longer than 20 delta. So antipodal points are distance at least 10 delta. But on the other hand, by Borsa-Coulomb, the f of n is equal to f of s, and therefore again by the triangle inequality, the distance in Z in the ambient space between n and s is at most distance from n to f of n, and from there to s. So it's less than 10 delta. That's a contradiction. The contradiction proves that the degree of the function cannot be 0. In fact, you can show the degree has to be 1. It's also obvious. And the particular function is onto. That's the part that we want. Once the function is onto, we know that every point of the circle B is within distance 5 delta that 5 delta over there of a suitable point of its inverse image under F in A. Okay, so we proved the lemma. Okay, so this is just sort of a usual yoga with triangle inequality, nothing surprising here. Now let's go on to collapsing the torus. Now suppose the torus T2.
And Misha, can I ask a quick question?
Yes.
Can you get that lemma to work for higher dimensional spheres instead of circles?
I think that this lemma is going to work. Yeah, this lemma is going to work. Whether or not the application is going to work, that's of course a good question. And by the way, I'm still working on surfaces. I still have open questions for the client model. So there's still work to be done. But I think the lemma might very well work for higher dimensional sphere. I don't see any reason why it shouldn't work. Yeah.
Thanks.
Now, okay, so now suppose the torus collapses to a circle. Now, which means that they both sit in the ambient space Z. So now the first estimate that we need is that the systole of the torus satisfies this bound, that the systole is less than 20 times the Gromov-Hausdorff distance from T2 to S1. So let's sigma denote a systolic loop of T. So we want to show that the length of sigma is necessarily less than 20 times the Gromov-Hausdorff distance between the torus and the circle. Now we choose a complementary loop, which is the shortest non-contractible loop in the torus, which is not proportional to delta, which is not proportional to the class of delta. So we choose a basis now. So then both embeddings are strongly isometric. That's easy to show. Not just sigma, but also mu is strongly isometrically embedded in T2. Because if it's not, it would be shortened. It's a simple argument. And they also meet transversely at a single point. And so because they have to meet by trivial intersection theory, they have to meet, and they have to meet transversely. And the smoothing out the intersection point, which shows that the homology class of their sum, you can choose a shorter representative there. And therefore, the shortest representative in that class also has to be embedded strongly isometrically, one could show. So now we have all three of these classes are now embedded strongly isometrically. So we can apply the lemma on the previous page to show that the map has to be injective, and that's of course impossible. So if this Gromov-Hausdorff distance denoted delta, if sigma is bigger than 20 delta, then all three of those classes are bigger than delta. They have to get mapped to non-trivial classes in the homology of S1. And therefore this homomorphism has to be injective, but that's impossible because this is rank 2, this has rank 1. And therefore the contradiction proves the lemma. Again, this is just a triangle inequality yoga. It doesn't use any of the geometry of the torus. So these three non-zero classes, and now we notice I replace the homology by Z2 coefficients. There are three non-zero classes here. So they're all represented by so sigma is represented by a closed geodesic of tiny length. That's the scale of the Gromov-Hausdorff distance between the torus and the circle S1. And the other two are of appreciable length because they are comparable to the diameter of the torus. So that's the picture here. And so just to fix ideas, choose mu to be the shorter one of the two. It's embedded strongly isometrically in the torus. And so now as a corollary, we see that if the torus and the circle are tiny Hausdorff differences in this common metric space Z, then every point of this one is a tiny distance from a suitable point of the closed geodesic mu. And this is just an application of the lemma to the pair of circles S1 and mu. So everything here is a tiny Hausdorff distance, mu, sigma, and the torus T2. So it follows that the torus is a tiny Hausdorff difference from the loop mu. And that's important to know that we didn't know in advance. So by the way, so far we haven't really used the curvature hypothesis. The non-trivial geometry of the Alexandrov space collapse is something that's coming up in the in the proof of the next theorem. Okay, so from now on, we're going to start using the non-trivial geometry of a Hausdorff collapse. Okay, so maybe let me stop here so people can ask questions. Are there any questions so far before we get into the heart of the proof? Unless I ran out of time already. Okay.
Oh, no, you have plenty of time. Questions so far?
I have a quick question, just a question for intuition. So if I remember, what you're saying about the torus isn't true for the Klein.
So what's the question?
What you're saying about the torus isn't true for the Klein bottle.
Right, the Klein bottle it can indeed collapse. It can indeed collapse to an interval, unlike the torus. Torus cannot, but the Klein bottle can.
Is there anything that you said so far that makes the Klein bottle case separate from the torus? In other words,
well, I think what you're bothered by is this: if you can after all collapse the torus to the Klein bottle. Torus, after all, is double cover the Klein bottle, and the Klein bottle, I said, can collapse to an interval. So why can't you look at the composition? And then there you have it. You have a collapse of the torus to a segment. Well, the reason that it's not true is because the image of a midpoint of the interval is going to be disconnected in the torus. So it's not going to be small. So that composition map does not give you a collapse to the torus to a segment. On the other hand, the torus can collapse in a different direction, so to speak, in an orthogonal direction, can collapse to a circle. But that's the difference there.
Okay, thank you.
Oh, you're welcome. So let's go on to the theorem. So the theorem says that if you have if you have a torus collapsing to so here we have the theorem. I just realized I suppose I should state the hypothesis of the theorem. We have a torus collapsing to a circle. Okay, well that's the situation we're talking about. I'll have to fix it if I ever give this talk again, unless I am booed at the end, in which case I won't. But in any case, so we have a torus collapsing to a circle. So we have this notion of tiny, small, and appreciable. So we have, if you take a small ball, notice that small is emphasized here. Send a small epsilon ball in the torus is necessarily homomorphic to an annulus. Of course, we don't, for the purposes of Alesker's conjecture, we don't really need it to be homomorphic to an annulus. But in any case, all we need is that it's homotopy equivalent to a circle. Okay, but in any case, that follows from it being homomorphic to an annulus. Okay, so the proof goes like this. A ball, of course, in 2 dimensions, you don't have much choice as far as topology is concerned. The only way that ball can be not homomorphic to an annulus if it has a hole, and the hole is because it has a finger sticking out. So if you have a hole, then if you lift it to the universal cover, it also has a hole. It's just basic topology at the level of Jordan curve theorem and that kind of thing. If you lift it to the universal cover, there's still a hole in the epsilon ball. So therefore, it's enough to show the epsilon ball in universal cover is homomorphic to a disk. In other words, it doesn't have holes in it. I'm sorry, I find myself having trouble speaking English. I guess I teach all my classes in Hebrew. I find myself having trouble completing sentences. Hope you don't mind. So in any case, right, so we have this ball in the universal cover now. So let capital P be the lift of P to the universal cover. Universal cover will denote by U. And let B denote the metric ball. Again, these are not homomorphic to disks. These are metric balls now, a metric epsilon ball. And we want to show that it's homomorphic to a disk. Suppose it's not. Okay, then B has a hole because there's a long finger sticking out of it. You're chopping off the long finger by the distance function. That's when you get the metric ball B. So here we're going to apply the Grover-Shiohama level that we mentioned in the previous slide. And you see that there's a change in topology here. There's a hole now, and that didn't used to be there before. When you start with the tiny ball, there are no holes yet, just because we're on the surface. And therefore, by the Grover-Shiohama level, there has to be a critical point of the distance function. Let's denote this critical point Q. and it's at a distance smaller than epsilon from P. And the typical case would be when Q is the midpoint of a geodesic loop based at P. So we have a geodesic loop based at P, and the midpoint, the furthest point from P along this geodesic is the point Q. That's what the example. That's one of the two examples that I mentioned for critical points. In fact, this is not only a typical case, but can actually prove that it exists. It has to exist in this situation, but we won't need that. Proving that it exists involves an application of Arzelà-Ascoli, which I'd rather not get into. So there's a more elementary argument. So if it doesn't contain a pair of antipodal directions, then you can always choose a pair of directions forming an angle of at least 2 pi over 3. And that's enough. Just choose a two minimizing geodesics between P and Q, which form an angle of at least 2 pi over 3 between them. And that can be, that's the two-dimensional case of, or the one-dimensional case of something called Jungs Theorem. But in any case, it's an elementary fact, but in any case, it's a special case of Jungs Theorem. There's always a pair of directions. If a subset of a circle is not contained in any semicircle, then there is always a pair of directions forming an angle at least 2 pi over 3. Okay, now gamma is a loop. That's a significant fact, because now you have a loop in U, which is topologically a plane. Therefore, it bounds a disk. It bounds a region D, which is homeomorphic to the disk by the Jordan curve theorem. This disk may contain some long fingers. Disk D a priori could be bigger than the ball B. Okay, so now we get to using our curvature assumption, the curvature lower bound of -1. Now, because of this curvature assumption, geodesics could not diverge very fast by Toponogov's theorem. So this allows you to control the how wide the torus gets when you get away from sigma. Sigma, remember, is the neck of the torus. It's the narrowest place on the torus, the systolic loop. And then afterward, the torus can start opening up, but it can't open up too fast because the curvature is bounded below. So it's a kind of it can open up like a horn, sort of a typical argument in Riemannian, thrust Riemannian geometry. Can you still hear me? Hello? Yeah, okay, good. Yep. So it can open up, but not too fast, at most exponentially in the length of mu. Mu, remember, is a complementary geodesic. That's the diameter of the torus. And so this is still tiny, because mu is only appreciable. Okay, so it follows from this that the disk D is contained perhaps not in an epsilon ball, at worst a 2 epsilon ball. So in any case, we have a handle on the size of how big this D is. And this will be used in the area calculation in a second. So now I apply the GaussManet theorem, my favorite theorem, the GaussManet theorem to this disk. Now, there's a difference in I think a difference between the Russian and the English literature. When you have a corner in your geodesic, you have a broken geodesic. Sometimes this change in direction is called a turn. I think that's the Russian literature. Or sometimes it's called a rotation. Sometimes that's the English literature. But in any case, what I mean is how much the direction of the geodesic turns when you pass through a point where it breaks. In any case, this turn or rotation, in any case, in the Shiohama Yamaguchi paper, it's called rotation. But I think Russian papers tends to call this turn. And in any case, this angle is always between minus pi and pi. So now, first consider just to write down the simple calculation. Let's go to the case when gamma, our famous loop, gamma is actually a geodesic loop based at P. So in other words, P is the only non-smooth point, and it's smooth at Q. Then we get the following lower bound by the GaussManet theorem. The curvature integral over the disk D is 2 pi times the Euler characteristic of D, which is known to be 1. Minus the curvature integral along the geodesic, the broken geodesic gamma. And where the curvature integral is understood in the path integral is understood in the generalized sense. At the broken point, you get a delta function, which is the turn at that point. But the turn is at most pi. is between -2 minus pi and pi, and therefore we get a lower bound for the curvature integral. So the curvature integral has to be substantial here. It has to be appreciable. So this is a key use of the GaussManet theorem here. Sort of a bit miraculous. So we get the appreciable lower bound for this curvature integral, even though we don't really have that much control over the metric. As we mentioned, there's no curvature upper bound, only the lower bound. So you could have spikes there, infinite curvature, but in any case, we have this lower bound. We have this lower bound for the curvature integral over the disk D. And okay, so now if Q happens to be not smooth, in any case, we still get, instead of pi, we get a lower bound of 2 pi over 3 by the same argument, by a similar application of Gauss-Bonnet. Okay, so how are we going to get the contradiction here? After you're looking for a contradiction, we want to show there couldn't be any holes. So we're going to show that this curvature integral is small. It could not be appreciable. And this contradiction, therefore, rules out the existence of holes. And this shows that our epsilon ball is actually homomorphic in the universal cover. Is homomorphic to a disk, and therefore in the surface itself it's an annulus. Okay, so how are we going to show that the curvature integral is small? So what we're going to do, we're going to pass to a cover of the torus. T sub n is the cover of the torus corresponding to the subgroup of the fundamental group is spanned by n sigma and mu, where n is sufficiently big. So this is how big you have to choose n. So you divide epsilon by sigma. Remember, epsilon is small, where sigma is tiny. So this epsilon over sigma is going to be huge, gigantic. And we multiply it by something that's only appreciable. It's not gigantic. And notice that I carefully avoid using words like infinitesimal and infinite because they tend to scare people. But okay, now I betrayed my allegiance to the cause. So in any case, so n is chosen in such a way that the region D actually embeds in this n-fold cover. The region D actually embeds in this n-fold cover, and therefore you can now perform sort of another miraculous calculation, an area calculation. And since the torus is orientable, so this is a fact from sort of first-year differential geometry graduate course, that sort of an interesting stability phenomenon, that this loop sigma tilde is also a systolic loop of the torus Tn. So in any case, it has small length n sigma. It's still a systolic loop, even though we passed to an n-fold cover. It's still the systolic loop, and its length. So the systole is still n pi n sigma, which does not happen in general. This only happens in codimension 1. In general, it doesn't happen. Otherwise, you have a phenomenon of systolic freedom, which I have a few papers on. Okay, but in any case, let's go on with the argument. So we decompose the Gaussian curvature as sum of its positive part and its negative part on the torus, on the n-fold cover of the torus. So K plus and K minus are positive and negative parts of K on Tn, on the n-fold cover of the torus. Okay, so now we're going to use these ingredients. GaussManet theorem, the curvature assumption, we're going to use it a second time. This calculation will also use the curvature assumption. And the fact that the torus has 0 Euler characteristic. Now, the curvature integral that we are interested in is, first of all, certainly less than the integral over the same domain of the positive part of the curvature. That's the first step. The second part, the domain D is contained inside the torus Tn, and therefore we get the second inequality. After all, we are now integrating a positive function. Therefore, we get this second inequality. And furthermore, by the GaussManet theorem, we know that the integral over the curvature of the positive curvature is equal to the integral over the negative of the negative part of the curvature. This is because the Euler characteristic of a torus is 0. So here we apply the GaussManet theorem to the closed surface called the torus. And now, because of the lower bound of the curvature, this integral is less than the total area of the torus. So you get sort of this miraculous global calculation, which gives you a local result. This curvature integral is now less than the area of the torus. Now, what's the total area of this torus? First of all, as I mentioned before, the diameter cannot grow too fast. It's on the order of mu. It's on the order of the Can I really prove that? Just a second. Maybe I should. Yeah, I can prove that. I didn't explain it here, but I can prove it. In any case, I was hesitating between mu and e to the mu, but I can prove that it's mu. In any case, it doesn't matter. So we use the closed geodesic sigma, this neck of the torus, and we use the normal exponential map. In other words, exponential map in the normal direction, and then we get an area bound by Toponogov's theorem, an area bound on the torus itself, which is sigma times nu times e to the mu, and that's because of the geodesics diverge. This is just Jacobi field estimates, Rauch's theorem type of thing. And then we're for the cover T, and we get this lower bound times n. And remember, n times sigma is sigma itself is tiny, and n times sigma is small. So we see that the area of the torus is small, and therefore the area of the region D is also small. And that's a contradiction, because earlier we showed that the curvature integral has to be appreciable, and now we show that it's small. Therefore, there couldn't be any holes. And therefore, the epsilon ball and torus are homomorphic to an annulus. Okay, that's the end of the proof of the theorem. Okay, and that's the end of my time also, so I will stop.
Thank you very much. Before we get to questions, let's briefly unmute ourselves and applaud for Misha.
Thank you very much.
And now questions.
One quick question is, I guess, so we have the torus and the Klein bottle. So what's true for the projective plane in terms of collapse?
Yeah, well, the projective plane is a different kettle of fish, because so here's the last screen about the Klein bottle. Here's an open question what to do about the endpoints. As I mentioned, the Klein bottle collapses to a segment. And using the kind of technique that I described, you can explain what happens for the interior points. So here you get a genuine complex. X is no longer a manifold, it's a complex. So you have to a stratified space. So you have to deal separately with the endpoints. And this requires additional work. I haven't finished working on the Klein bottle yet. But the reason I mentioned this is because Klein bottle also happens to have Euler characteristic 0. And therefore, the same kind of technique allows you to handle it as the torus. Remember, using an essential way, the fact in the area calculation, the fact that the Euler characteristic is 0. Now, the Euler characteristic of the real projective plane doesn't happen to be 0. So this technique doesn't work. And the same goes for the sphere, by the way. The sphere and the projective plane both can collapse to a segment, but this technique just doesn't work, and you have to look for other techniques. And one technique that Alesker mentioned is you can use there's something called the Pogorelov embedding, but that only works, or the Weil-Levy embedding, but that only works for positive curvature, positive Gaussian curvature. But there's a more general result called the Alexandrov embedding, where you embed in hyperbolic space. And there you can actually embed your sphere into also, but into hyperbolic space, not into Euclidean space. And that's very helpful, because then you can cut by distance ball. So then you have nice mention of distance ball in the hyperbolic space. So you can start cutting your surface by distance balls, by hyperbolic distance balls, and then you can start proving things. We haven't finished this because I was still busy with the torus and the Klein bottle, but I'm pretty optimistic that it'll work for in these two cases also. Other than that, I have certainly not the choice to prove it, but I happen to have published a paper dealing with the case of surfaces of negative Euler characteristic, which cannot collapse in this sense. Okay, so after that, as you mentioned, we have to start looking at manifolds. Now, one nice thing about it is that Yamaguchi sort of everybody thinks that Yamaguchi makes all these things trivial, but it's sort of a magic wand that, first of all, is very expensive. Their latest paper is 60 pages, which is not unusual by Gromov's standards. Gromov's filling paper was 143 pages, 147 pages, but it's still a long paper. It's a lot of work. Now, the case of surfaces, of course, much easier, but in any case, it's a lot of work. But it doesn't. Another property of this magic wand is that it doesn't give you exactly what you want. It's, Zamora published an article on the Taurus, and there you still have to put in work even after you assume Yamaguchi fibration. You still have to do some work in order to prove that the Taurus doesn't collapse to an interval. But you can also, another way of looking at it is sort of this kind of application of GaussManet sort of shows you why Yamaguchi works in the first place. That it works for surfaces that we can expect it to work in general. Anyway, the Shiohama Yamaguchi paper is in dimension 3, and I heard I'm far from being an expert in the field, but apparently there is also results in dimension 4. But I think that's where the buck stops right now, at least if you want to deal with the general case. I think there's a Yamaguchi result works if you assume the bottom to be a manifold, and you still get an almost Riemannian fibration, in the sense that it's 1 plus epsilon by Lipschitz in the direction of horizontal planes. But the general case, I think, is open in higher dimensions.
Thank you. That's a very thorough answer.
Thanks.
Further questions?
Yes. Thanks for the talk. So maybe I missed it, but it is not clear
Please
to me.
speak louder. Next time I'm going to get.
Oh yes. Sorry for my microphone.
Using the speaker of the camera. So
please. Is it
speak
better
up.
now? Is it better now?
Yes, now I can hear you.
Okay. So thanks for the talk. I may have missed it, but it is not clear to me where integral against Euler characteristics comes in or appears.
Can someone translate? I'm sorry, I didn't make out what he said. Henry, can you try to? What did he ask?
So
Sorry.
He asked if you could say more about where integration against Euler characteristic appears.
Yes,
Thanks.
no, the integration against the Euler characteristic is a certain, it's, by the way, a discrete integration against the Euler characteristic. Discrete integration.
Yes.
So it involves something they call, again, I'm far from being an expert in the field, but the words that they use are like this. They have something called the constructible function. This is a certain integer valued function on the strata.
Yes.
The simple case still appears on the screen here. We have an interval which has 3 strata. It has the interior edge and it has the 2 endpoints. And you have to deal with them separately. And the constructible function is going to have different values according to strata. In case of the Klein bundle, it might actually have the same value, but in principle, they have different. And the other ingredient in the formula is the homotopy type, or even weaker, the Euler characteristic of the fiber over the stratum. That means you take a point on the stratum and you look at a ball around the point and you look at it intersections with the manifold that's collapsing. And that homotopy type, you need to show that homotopy type is well defined. This is what I proved in my talk, right? This is what I proved in my talk. I proved that the homotopy type is well defined. I proved something that's slightly stronger, that the epsilon ball is actually homeomorphic to an annulus. In particular, it's homotopy equivalent to a circle. Okay, and so it has Euler characteristic 0. That's the ingredient that you need for the discrete integration against Euler characteristic. And the other ingredient is the constructible. This is what they call the constructible function. And the formula is that when you have a manifold collapsing to a complex, then the limit of the Euler characteristic of the manifold is going to be the sum over the stratified space X of this constructible function times the Euler characteristic of the stratum. That's the formula. That's the conjecture formula. This formula, by the way, exists in algebraic geometry. It's called, I think it's related to something they call vanishing cycles. But Alesker has a generalization of this in the case of the Alexandrov space collapse of the type that we discussed today. But in any case, that's still conjectural. For surfaces, it should be immediate from once one settles the remaining cases. There are only 4 cases here for surfaces that can collapse to one-dimensional complexes: the torus, the Klein bottle, the sphere, and the real projective flame. So there's not much novelty in proving the integration. But in any case, this is sort of a baby case of trying to prove that the ingredients of the formula for discrete integration against the Euler characteristic actually make sense. That there's a well-defined homotopy type of the fiber.
Thank you very much.
You're welcome.
Further questions? Let me ask a question, Misha. So this is a question about one of the tools you used, which is the notion of critical points of this distance function, distance to a point. So you mentioned that you have this sort of Morse lemma. In the absence of a critical value, the homotopy type doesn't change. Are there many tools along the lines of sort of the other Morse lemma, which is when you have an isolated critical point, can you say anything about how the homotopy type changes?
In other words, you want to push through more of Morse theory than just deformation lemma.
Yeah, or is this possible, or have people looked at this, or if this is hard, could you say why it's so hard?
Well, look, in the way what I did today is a kind of I basically proved the mountain pass lemma. You remember when I said that we can construct the geodesic loop gamma based at P, whose midpoint is Q. That's a kind of a mountain pass lemma. We didn't actually prove it. As I mentioned, we don't really need it. But it is a kind of a mountain pass lemma. There you're sort of adding a critical point of index 1.
I see, and attaching a one cell in some sense.
Now, it would be interesting to see what happens in so I have to, I published this paper on neighbors of the Kuratowski embedding. By the way, I was the one who introduced the term Kuratowski embedding.
Ah, fantastic.
I coined that term. It appeared in the title of my paper from 1991, and now everybody calls it. It's nice that it was a successful coinage. But in any case, so I guess I still have to, Pansu published the famous Green Book, the Gromov's Green Book. And then a lot of people complained that there are mistakes in it, there are arguments that need to be filled. So Pansu used to joke that we need to provide the service après-vente. Service après-vente. Anybody here speak French? Service après-vente. How would you translate that into English? I guess after-sale service. You need to provide customer service after sale. So I guess I have to do the same with my Kuratowski embedding paper. I guess I was imitating Gromov's telegraphic style, but now, which is more than 2 years later, I have to figure out what I meant. So I guess Facundo and I are supposed to look at it at some point. We have to see. Even in the case of a circle, I have to figure out what's going on there. And that also is a kind of a higher Morse theory going on there. With the connected components merging together, you have to understand what the next homotopy type is. So you go from circle to the 3-sphere to the 5-sphere, etc. So this idea is basically in my 91 paper.
Right.
You wrote a very nice paper where you filled in all the missing dots to get the full KZ1.
Although I haven't told my graduate students yet that they need to provide customer service for all the mistakes that will be found in my papers, but they'll soon learn that, I suppose. So.
You mean there's customer service for that paper also?
No. I don't know of any errors in that paper, but math is always evolving, right? So.
Okay. So thanks very much. It was a pleasure speaking here.
Yeah, thank you so much. Really appreciate it. Let me end the recording here.